Okay, so what we're looking at here is the calculator for RSRQ that I've put together. Looking at the various forums and so on, it certainly looks like there's some confusion over things like RSRP, RSRQ, RSSI, and so on. So I put this little calculator together really just to explain it to myself, and I thought I'd share it with you guys. So, well, first of all, we're going to look at, well, this area that you're looking at here is really just some representation of a resource block. So, of course, in this case, we've got, 6 time domain symbols, and we have 12 frequency domain symbols in here. Now, the orange areas that you see in here are the 2 resource elements that will contain the reference signals, and the remaining green areas that you see here, in fact, are the resource elements that just contain power present from general traffic coming from the serving cell, coming from the neighbor cells, and so on. So it's within this time domain symbol, those time domain symbols where the reference signal is present, where the mobile measures both the RSSI and the RSRP. Now, there is a difference in the measurement that the mobile makes in this case. So looking at RSSI first of all, when the mobile makes a measurement of RSSI, in fact, it makes a measurement of the total power present in all of the symbols. So in this case, all of the sub-channels, all of the frequency domain symbols. So it measures the total power present in all of those. So that's the resource elements that contain potentially traffic and interference, and in this case the red cells that you see here, which also contain the reference signals. Now, in this case, I'm showing a slightly theoretical scenario here where, in fact, the load is at 0%. So you can see here I've got the load set at 0%. Now, this actually indicates that we're looking at a serving cell example only, so the mobile is effectively connected to a serving cell only, and it's only measuring really the total power present in the reference signals, because there is effectively 0 power present in the remaining resource elements in this case. So given that we've got some sort of nominal transmit power of, I've just put 1 watt in here, it doesn't really matter what the transmit power is, because the RSSI, RSRP and RSRQ are all relative to each other, so it doesn't really matter what value we put in there. So in fact, in this case, we're looking at, well, there's 0.017 watts. That's the total amount of power present at the time at which a mobile will make an RSSI measurement. So again, really what it's doing here is just looking at, well, in fact, the only power present at this point is in the reference signals, because the load is 0%. In this case, we'll play around with the load setting in a moment or two, but if we just consider briefly the RSRP value here, so looking at RSRP, now RSRP is a different measurement to RSSI because, well, for one thing, the RSRP measurement, this is of course the reference signal receive power, it only measures the power present in the time domain and frequency domain symbols where the reference signal is actually present. So in fact, it's only measuring the power in this case in the 2 sort of red or orange symbols that you can see here. It is importantly the average power measured in both of those symbols. So it's going to measure the total power, if you like, measured in reference signal symbol 1, reference symbol 2, and then it will take the average of that. So we can see in this example, because of the way the power is set up at the moment, there is 0.083 of a watt present in each reference symbol. Of course, then the average of 2 measurements taken there would be 0.083. So in this rather theoretical case where there is a 0% load, so there's no traffic, the only power present in fact is there's that which is present in the reference signals, that would result in therefore an RSRQ of minus 3 dB. The reason it's minus 3 dB is because the RSSI which is measured is the total power present, which in this case is just 2 reference signals, so that's the total power present in the 2 reference symbols, and then we have the average power measurement across those same 2 reference symbols, in this case 0.083. So the basic calculation for RSRQ is the RSRP linear power, so of course it must be in watts, divided by the linear power of the RSSI. So 0.083 divided by 0.017 converted into logarithm will give you minus 3 dB. This is a very theoretical value because it assumes, of course, there's no load present, no real traffic present. But it'll give you an idea of what the expected range of RSRQ values will potentially be. So the next thing to do then, it really is to indicate some load in the system. Now, when we indicate the load using this cell here, this is really just load from the serving cell. Okay, so we're pretty much ignoring any adjacent cells, any potential interference and so on that might be present here. So in this case, what we're going to do is we'll load the system with 30% traffic, and what you can see in here now is that in fact I've only got 3 of the resource elements actually carrying traffic in this case. So all of the red cells that you see in this case now, which are labeled 0, are basically carrying no traffic, therefore no power. So it's a very theoretical mathematical model in here, but it gives us an idea now that the total RSSI measured is now the 3 green cells that you see here, the actual traffic itself, plus the 2 orange cells which represent the RSRP, the reference signals of course. So we have a total power present now of 0.42 of a watt, RSSI measurement, and the RSRP measurement of course stays the same. So this then results in an RSRQ measurement of minus 7 dB. If we step the load up a little bit more, so we go to 60%, so you can now see we're filling approximately 60% of those resource elements with traffic. The measured RSSI, of course, will increase because there's now more power present in there, and we now have an RSRQ value of minus 9 dB. Now I'll step just quickly through to 100%. So now we're looking at a resource block which is 100% loaded, and again it kind of makes sense here that if we're transmitting 1 watt across the entire resource block and we measure the RSSI here, then we will measure the total amount of power present across those 12 symbols, therefore the total must be 1 watt. The RSRP power still hasn't changed, it's still 0.083 of a watt because it's the average power measured across those 2 orange symbols over here, and the RSRQ, the resulting RSRQ in this case, is minus 10.8. So in the presence of a serving cell only, therefore discounting any sort of adjacent channels, so in the presence of only a serving cell, where we're effectively discounting the presence of any adjacent cells, and that serving cell is loaded at 100%, the range of RSRQs that we'd be looking for would be no worse than about minus 10.8. However, in a real network there will be adjacent cells and they will present some sort of interference to the system. So I've tried to model this very, very simply here with this sort of scaling factor. So what we can do here is we can actually add a certain amount of interference into the system, which will result in an increased RSSI measurement in this case. So I'm going to add here just a scale of 0.2. Now in this case you can see that the RSSI measurement is actually now greater than 1 watt. So that's an indication that the total power collected by the receiver is the 1 watt of power coming from the serving cell plus some additional power which is leaking in from the adjacent cells. So you can begin to see now the RSRQ is getting worse than minus 10.8, which was sort of our best figure for a 100% loaded cell. So I'm going to add a bit more interference and you can see what goes on there. So we'll go up to a 0.5 scaling factor here. So now we're out now at minus 13 dB. If you're making these measurements in a real network and you're getting, as I said, worse than 10.8 dB, then that does indicate that there is external sources of power, therefore interference, actually present. If the serving cell itself is highly loaded and the adjacent cells are also highly loaded, this is when the RSRQ value begins to deteriorate. So in order to compensate for that, one thing that's available to the operator, I mean this may depend on the vendor of the base station and so on, but it's pretty typical that you'll be able to boost the power behind the RSRP. So I've got a very simple option here. At the moment we have 0 dB power boosting, and so the reference signal power is effectively the same as all of the other resource elements of the serving cell. But if we boost that power by 3 dB, so that's 3 dB more power will be put into the reference signals, symbols. Now because we only have a 1 watt transmit, then of course that 3 dB power extra that we're putting into the reference signals must be borrowed from the resource elements carrying the traffic. So we'll get more power in the reference signals but less power in the serving cell resource element. We can boost the power by 3 dB. So what's happened is we've now got a much better power level behind the RSRP, and in fact you can see here we've improved the RSRQ by well, around about 3 dB. In a network which is highly loaded, therefore a very high probability of interference in the system, so poor RSRQ, providing an RSRP boost does in fact improve the RSRQ value. Now both the RSRP measurement and the RSRQ measurement taken by the mobile can be used to make mobility decisions. Now when you look at the idle mode cell reselections, it's predominantly the RSRP value that allows the mobile to make those serving cell, neighbor cell reselection decisions. But when the mobile is actually in a connected state and it's required to report values back into the base station, it can be requested to report both RSRP and RSRQ. So in fact the RSRQ is quite an important parameter to allow the base station to judge the overall signal quality from the point of view of the mobile device. So of course we can provide handovers on the basis of a quality threshold, RSRQ, or purely a signal strength threshold like the RSRP. Now there's another thing that we're looking at in this particular spreadsheet, and this really relates to the tables that you can see at the bottom here. Now when you're actually in the field taking measurements, it will be apparent that there is a very large difference between the actual RSSI that you measure and the RSRP. So to try and model that in a slightly more realistic fashion, what I've got here is an input of the number of resource blocks. So basically this is an indication, of course, of the actual channel bandwidth. Again, we can indicate some sort of power that we're putting into the entire carrier. So my example of just 1 watt here, in fact, is 1 watt being pushed into 25 resource blocks, which of course is in this case 300 sub carriers. So the power per subcarrier, you can see in there 0.0033 watts, and of course the power in the reference signal would be the same in this case. Now what I've worked out here is the number of subcarriers that carry non-reference signal information. So there's 250 of the 300 available to us in this particular example. 250 of those will never carry reference signal information, but 50 of them will periodically carry the reference signal information. You were able to work out then what the power contribution is between the non-reference signal subcarriers and the reference signal subcarriers. So in this table here, or in this particular cell, I've just got some nominal value of path loss. So of course we know what the radiated power is, 1 watt in this case. We're able to work out therefore what the RSSI should be on the basis of that path loss. So we are effectively transmitting, you can see here, 30 dBm, so that's 30 dBm behind 300 subcarriers. When we take an RSSI measurement, which will be across the subcarriers, so that's all 300 of them, we would measure minus 100 dBm. So I guess that kind of makes sense. We're transmitting 30 dBm of power. We're losing 130 dB of power across the link. Therefore, the RSSI, the total power measurement across the channel, is minus 100 dBm. The RSRP, though, because the RSRP is only measured across 50 of those channels, again there's a particular ratio here that means that the RSRP will always be a lower measured power than the RSSI. The amount by which that measurement differs really is a function of the channel bandwidth, so the number of resource blocks, the number of subcarriers used to transmit that information. When it's a 5 megahertz channel and we're using 25 resource blocks, there will always be something in the order of a minus 24, 25 dB offset between the two. So if you're measuring an RSSI of minus 100 dBm, the RSRP will be consequently around about minus 125 dB. Now I'll just quickly change the number of resource blocks here, and we can see the difference in the different channel bandwidths. So we'll go for, in fact, let's just jump straight for a 100 resource block. This is, of course, a 20 megahertz channel in here. So you can see there is now an offset, a difference between the two of around about 30 dB. The RSSI measurement hasn't changed because we didn't change the transmit power of the path loss, so we're still measuring minus 100 dBm for the RSSI. But you can see that the RSRP now will be around about minus 130 dBm. So there's effectively a 30 dB offset between the RSSI and the RSRP. Okay, thanks very much for watching this. I hope that's managed to clarify some of the confusion over RSSI, RSRP and so on in there. It is just a very simple model, but I hope you found it interesting and maybe even useful. So thanks very much.